Hello, my dear students. I welcome you again in the next lecture, the lecture number 2, in the topic of majorly basic feasible solution. In this lecture, at first, we will try to see several possibilities or several nature of the solutions of linear programming problems. Once we find out the different nature of the solutions of LPPs, we will try to characterize the natures with the help of some conditions in the objective function and in the constraint set. That means precisely with the help of the values of the objective function C transpose X. By values I mean by this given C, you have the objective function as maximization of C transpose X. Here C is a given value in the problem, as well as in the constraint set you have Ax equals to B, and once you have X equals to B, you have these informations, the coefficients, the entries of the matrix A and the entries of the matrix B. With the help of the entries of the matrix C, of the matrix A, of the matrix B, we will try to identify some conditions satisfying which you will be able to check different natures of the solutions of linear programming problems. At first, we will try to look at exhaustively the possibilities of having solution of linear programming problems. Then we will look at the fundamental concept in solving the linear programming problem, that is the notion of basic feasible solution. And in between, the concept of degeneracy of a solution, or specifically degenerate basic feasible solutions, will be considered to be taught in this lecture. Towards the end of the class, we will try to find a condition satisfying which we will be able to confirm the possibility of having maximum possible basic feasible solution for a given system of linear equalities. Fine. So, in order to identify several varieties of the solution, several nature of the solutions of LPPs, what I will do here, I will mention specifically 7 problems of different natures, 7 linear programming problems, from where the exhaustive variety of the solutions will be identified, and then we will be concluding by mentioning the nature of the solutions of an LPP, and then we will jump to the topic of identifying conditions satisfying which different natures of the solutions of the LPPs can be identified. So let me quickly mention 7 problems of LPPs. Obviously the problem that I am mentioning here, those will be of 2 variables, so that you can graphically solve them out, and I guess you all have gone through the graphical method of solving linear programming problems in your high school, and therefore I will obviously not discuss here the graphical method of solving a linear programming problem. Rather, I will just give you the problems, I will also give you the solution. Let you verify graphically that the solutions are correct. And from the solutions, from the geometrical perspective of the feasible set or the constraint set of the problem, we will be mentioning that the possibilities of the nature of the solutions of LPPs. So the first problem that we will try to consider is the one which is asking you to maximize (150) x1 plus 100 y, sorry, x2, and subject to 8 x1 plus 5x2 less than equal to 60, 4x1 plus 5x2 less than equal to 40, together with the non-negativity restrictions on the variable x1 and x2. For this problem, you all will be able to identify that for this problem, you graph out the feasible region, that is the set of all possible points x1, x2 which satisfy both the inequalities together with the last non-negativity restriction. And here you will find that the optimum solution is x1 is equal to 5, x2 is equal to 4, and the objective function value, if I denote this objective function by z, then z max is equal to 1150. This is your optimum solution for the problem, and this problem has only one solution. Second problem is the following. It is asking you to minimize z equals to 3x1 plus 5x2 subject to 2x1 plus 3x2 greater than or equals to 12 minus x1 plus x2 less than or equals to 3, x1 less than or equals to 4, x2 is greater than or equals to 3. This problem. And for this problem, you will find that the optimum point is x1 equals to 3 by 2, x2 is equal to 3, and z min is equal to 19.5. This is your optimum solution for the problem 2. Next problem we will consider is minimize z is equal to x1 plus x2 subject to 5x1 plus 9x2 less than equals to 45, x1 plus x2 is greater than equals to 2, x2 is less than equals to 4, together with you also have the restrictions x1 greater than equals to 0 and x2 greater than equals to 0. For this problem, the optimum value here to find, if I just quickly give you the graph of the feasible region, you will find that the graph is as follows: 5x1, so here if this is my location 9 unit, this is my location 5 unit, this is your x1 axis, this was your x2 axis, then you have here 5x1 plus 9x2 is this set. This is the line and the next one plus x2 is this line. That is your 2 unit, here is your 2 unit, and this is the line. x2 is less than equal to 4, so here is 4 unit, x2 is less than equals to, okay, x2 is less than equal to 4, so x2 is here, x2 is here. So this will be your feasible region, you all can check. And in this feasible region, you find that the minimum value will be obviously, as this line is your x1 plus x2 is equal to 2. So the minimum value of the objective function in this dotted region is obviously 2, and there are infinitely many solutions, infinitely many optimum solution. Any point in this line segment in between these 2 points, that 0 2 0 2 is here and 2 0, any point in this line segment are optimum point for this problem. So there are infinitely many optimum solutions. Fine. In the fourth problem, we have to maximize z equals to 3x1 plus 4x2 subject to x1 minus x2 is greater than equals to 0, minus x1 plus 3x2 is less than equals to 3, x1 is greater than equals to 0, x2 is greater than equals to 0. And for this problem, if we try, you just try to figure out the feasible region. Here I repeat the notion of feasible region from the last day's lecture. You note that by feasible region, I mean the constraint set. Constraint set or the feasible set is the set of points x1, x2, which are satisfying all the restrictions. So set of all points x1, x2 in the two-dimensional Euclidean space. That means in this x1, x2 plane. Set of all points which are satisfying all these restrictions. That region is called the feasible region or the constraint set of a given linear programming problem. For this problem, if we quickly try to find out what is the feasible region, you will find that here is your x1 minus x2 is greater than equals to 0. Here is your this line x1 is equal to x2, and x1 is bigger, and therefore the region over here is this region, this side and this side. And for minus x1 plus 3x2 less than equals to 3, you have minus x1. So here in the negative side is your 3 unit, and then suppose it is your 3, and here is your 1. Then the feasible region obviously is your this line, it will intersect somewhere here, and then it will go away this, and let us straighten it, x1 equals to x2, and the feasible region is this region, and this feasible region is unbounded, right? And here the objective function can be made bigger than any number that you can think of, and so this objective function blows off in the feasible region. Fine. So this objective function line can be just moved away from the origin indefinitely, and hence this problem has unbounded solution. Fine. Then next we'll consider a problem where you have to maximize z equals to 2x1 minus 3x2 subject to x1 plus x2 less than equals to 2, 2x1 plus 2x2 less than equals to 8 together with non-negativity restriction. For this problem you will find that the feasible region is an empty set, and therefore no sorry it will be empty set provided you take here greater than equals to 8, greater than equals to 8. And in this problem you do not have any point that satisfies all the inequalities, and such case is called there is no feasible solution of the problem. Find so no feasible solution. Then the last problem is a maximization problem. 6x1 plus 4x2 subject to 7x1 plus 5x2 less than equals to 35, 5x1 plus 7x2 less than equals to 35, 4x1 plus 3x2 is greater than equal to 12, 3x1 plus x2 greater than equals to 3 together with the non-negativity restriction x1 x2s are greater than equals to 0. For this problem you will find a solution, optimum solution, but you will see that here some of the constraint, precisely this constraint, is redundant in nature. Even if you do not have this constraint, then also the feasible region is the same, and such case is called redundant or redundancy. In the constraint set. Fine. So if I just look back and collect the possibilities of solutions, in the first problem we know that we have a unique solution. In the second problem also we have a unique solution. In the third problem there are infinitely many solutions. In the fourth problem the solution is unbounded. In the fifth problem there is no feasible solution. That means in the constraint set is empty set. And in the sixth problem there is a redundancy in the constraint set. So these are the nature of the constraint set and the optimum solution of a linear programming problem. So if I just collect them and note them out, you will find that there are 5 possibilities of nature of solutions of LPPs. Those are: the first, unique solution. There is a unique solution and finite. unique solution, and the solution is a finite and definite quantity, then there are infinitely many solutions. Then there is a possibility of unboundedness of the feasible region. Such case is called as there is unbounded solution of the problem. Then there may be infeasibility, so no solution exists. Then the last is there is a unique solution may not be feasible. Fine. So it is also called infeasibility of the constraint set, or this is also under the umbrella of no solution of the constraint set. Constraint set. So let me put this no solution inside fourth, and in the fifth there may be redundancy of one or more constraints. One or more inequalities or equalities, that is called as constraint. One or more constraint. Any particular equality or inequality in a linear programming problem is referred as a constraint. So for instance, for this problem, how many constraints are there? First constraint, then second, third, fourth, fifth, and sixth. So there are six many constraints on the problem. So here by redundancy we mean there exists at least one of the constraint which is redundant in nature. That means without having, so that particular constraint does not have any effect in the feasible region. Even if that constraint is not there, then still the feasible set is the same. That's why the nomenclature redundant. Anyway, so these are five possible nature of the solution of LPPs. Now question comes, here you note that for a two-dimensional problem, for a two-variable problem, we can just quickly graph out the feasible region, and we can find out the solution with the help of the graphical method. And this is a very easy task. You just graph out the inequalities and then you check where the optimum solution can arise. But this way of solving, this graphical way of solving linear programming problem is not valid more than three variable problem, right? And therefore when you cannot graph out, or where there are many number of constraints, in that case obviously the redundancy, infeasibility, or unboundedness is very difficult to trace out. Just by manipulating the inequalities you will not be able to, or it is rather very tedious and difficult to identify some infeasibility or some redundancy of the constraint set. And therefore we have to find a mathematical condition, if possible, satisfying which we will be able to check that the problem is having unbounded solution, or the problem will have a unique solution, or any of the five cases. And so we now start our journey to identify some conditions satisfying which we can ensure, and this condition obviously will be depending on the given information of the problem. By given information, obviously, for a linear programming problem, the given information are only three. That this vector C, this matrix A, and this vector B. So depending on these three matrices, which are the known information or the given information of a linear programming problem, let us now try to identify in which category out of the five category the problem, your given problem, will be falling in. And in order to find that, we require an efficient technique to solve the constraint set. By solving constraint set, we mean that, as I have said, as I have mentioned on the last day, all the theoretical discussion will be done only on the standard form of linear programming problems. And in the standard form, you have this maximization c transpose x subject to x equals to b, together with you have the non-negativity restriction. This is your standard form of the linear programming problem. And in this standard form, mm, uh, all the theories that will be described later on, all the theories will be just only on this standard form. And in this standard form, we observe that the solution, obviously, the solution of this problem, that means the point x bar or x optimum, which is the optimum solution, or which gives the maximum value of the objective function, obviously is a solution of this system of linear equalities. It's not that. And therefore, in identifying an effective method to find the solution of a linear programming problem, we have to find some way, some effective way to find a solution of this system of linear equalities. So efficiency of a method to solve a linear programming problem is exclusively dependent on a method, an efficient method to solve a system of linear equalities. And therefore, next half an hour or quite an amount of time, we will devote ourselves on finding solution of system of linear equalities. We note that in our mathematics 2 course, we have learned the existence of solution of a system of linear equalities. If some of you have attended the course of numerical techniques, there also you have learned the topic called Gauss elimination process, Gauss Seidel process. So those processes were the process to solve a system of linear equalities. We note that the Gauss Seidel process, Gauss elimination process, those process ended up in the numerical techniques ended up finding just a solution. But effectively, for a linear programming problem, you will find that just one solution will not be enough. Because here we note that if I geometrically try to find the feasible region, and we note that this feasible region, obviously this is a converted, the standard problem is obviously a converted problem from the usual or the natural form or the canonical form. In the canonical form, we note that we have the constraint set given by ax less than equals to b, and then by adding some slack or surplus variables, ax plus some slack or surplus variable, I is a matrix consisting only the diagonal entry is 1 or minus 1, with the slack or surplus variable vector s you have equal to b. So that equality constraint is written over here. Don't be confused with the same x with the x over here. So without loss of generality, let us suppose this is our original problem. This is our standard problem, and the original problem was having the constant set x less than equals to b, and inside of x less than equals to b we have precisely m many inequalities. And what are those m many inequalities? In x less than equals to b, you have a11x1 plus a12x2 plus till a1n xn is less than equals to b1. This is your first constraint. Similarly, the second constraint will be less than equals to and all. Have you note that corresponding to the first constraint, you have one inequality region, and that inequality region, let's suppose, is this side of the line. Fine. Similarly, for other inequality, let's suppose this side is my feasible region, and for other inequality, let's suppose this side is my feasible region, and therefore this will be your constraint set. So the constraint set or the feasible set of a linear programming problem is obviously a polytopic region. It's not that. So it is a polytope kind of thing. Polytope, by that I mean it is a hexagon, pentagon, or n-gonal region. Fine. So many gonal region it is, and particularly maybe a triangular region, maybe a parallelogram, or a hexagon type of figure. Those are the figures or region or the set that represents the constraint set of a linear programming problem. And therefore we note that effectively there are infinitely many solutions to this system Ax equals to b. Fine. Once you have infinitely many solutions, somehow we have to filter out what are the possible candidates of solution for the given linear programming problem. We will prove one day that these are the precisely these kinks or the vertices of the feasible regions are the possible points of optimum solution. Fine. And therefore this is our geometrical observation, and therefore mathematically we have to at first certify that only the vertices are the possible candidates of being optimum for a linear programming problem. And before that, obviously, to identify an effective way to solve a linear programming problem, we need to find some effective way out to solve efficiently the system of linear equalities. So let us devote a few time for the solution of a system of linear equalities. System of linear equations. It is precisely this system we are trying to talk about. Ax is equal to b. Very simple. And here the A is a matrix and its entries are Aij of order m by n. B is also the column vector, which can also be presented by m by 1 matrix, and the matrix A can also be presented by first column A1, second column A2, and the last column is AN. Fine. So this is your system. Ax equals to b. It has precisely m many equations. Fine. And here, as you all know, this matrix A is called the coefficient matrix, and associated to this system we refer the matrix A adjacent to B is called the augmented matrix. Here, as you all know, under which condition a system of equations will have a solution. As you all know, that condition is with the help of very simple rudimentary rank analysis of matrices. You know, a system of linear equalities is having a solution if and only if the rank of the coefficient matrix and rank of the augmented matrix are identical. So for the consistency or having a solution for the system of equations requires the condition the following: consistency, or this system is called consistent if there exists one x which satisfies x equals to b. So consistency is related to having a solution of this system of equalities. So it is consistent if for the consistence for consistence we have we need to have rank of the matrix A and the rank of the matrix augmented matrix AB, they are same. And otherwise, if the ranks are not same, rank of the coefficient matrix and rank of the augmented matrix, if they are different, then the system is inconsistent. There does not exist any x which satisfies ax equals to b, which satisfies all the constraints, all the equalities of this system. Fine. Now let me try to talk about several possibilities of having a solution. So by several possibilities, I mean provided the system is consistent, let us try to analyze the values of these m and n, the dimension, the order of the matrix, and the rank of these two rank of coefficient and the augmented matrix. Let's suppose this is equals to k. Let us try to analyze the values of k, m, and n. Let us try to interrelate them. Once the system is consistent, whether that system will have a unique solution or there are infinitely many solutions. And for that we all know the result. Let me just mention you the result. So we are under the assumption that the system is having a solution. So the system is consistent, and once the system is consistent, then we note that a given system can be horizontal rectangular. By horizontal rectangular, what do I mean? By horizontal rectangular, I mean it is of this form, that number of variables are more than the number of equations. So if this is my system, that the matrix A is having A11, A12, A13, A21, A22, A23 of this type, where you have the number of variables x1, x2, x3 is bigger than the number of equations. First equation, second equation. Here is your B1, here is your B2. So this is called as horizontal rectangular system. This is called a square system if the number of equations and number of variables are the same. So if we have this case that it is horizontal rectangular system, so it requires the condition, obviously the number of variables n is bigger than or equal to the number of equations. This is one possibility. Another possibility is that the system might be vertical rectangular. That means the number of variables are smaller than the number of equations. For instance, we consider this particular system where you have first row A11, second row A12, first row is this A11, A12, second row is A21, A22, third row is A31, A32. Fine. And then x1, x2, and here goes one, first, second, and the third equation. So if your number of equations are more than number of variables, then we call it is vertical rectangular system. So if you have n greater than equals to m, then let us try to analyze whether the system will have infinitely many solutions or it may have a unique solution. So here we analyze the following cases. So the first case is the case 1, where the system is horizontal rectangular. That means n is greater than equals to m, and it is given that the system is consistent, and therefore so n greater than equals to m, and rank of the matrix A is equal to rank of the augmented matrix, and this is equals to k. Obviously, as you all know, this value k is always less than equals to the minimum value of m and n. So k is less than equals to, as you all know, this is your minimum of m and n, the number of rows and number of columns. And therefore, so once you are in under this assumption, then this will imply that k is less than equals to m. So this implies k is less than equals to m. Now here can be two cases, two sub cases. So the first subcase A, which is your if k is equal to m, and another case is subcase 2, subcase B, where k is less than m. Now if k is equal to m, that means the rank of the matrix A is equal to the number of equations. And in this case, what will happen? In this case, we note that once the rank is equal to precisely equal to the number of equations, then you note that you just assign the variable value. Let's suppose this submatrix, as the rank of the matrix is equal to m, and let's suppose this matrix here, this 2 by 2 matrix, is having determinant non-zero. Then you take the value of x3, any particular value, and accordingly what will happen, you will obtain the value of x1 and x2 uniquely. For a very fixed value of x3, you will keep on getting the values of x1, x2, and therefore by varying x3, you will be obtaining infinitely many solutions. And therefore for k equals to m, this system will have infinitely many solutions. The system has infinitely many solutions. Fine. And for k less than equals to m, that means the number of the rank is less than the number of equations. So for instance, if I have this 2 by 3 system, and in this case if the rank is equals to 1, so another equation is just redundant. That means that another row of the matrix A is linearly dependent to the other row, and in this case what will happen, one particular row is completely redundant, and therefore obviously it will have again infinitely many solutions. The system has infinitely many solutions. Although all this rank analysis and these case subcases are not directly influential in finding basic feasible solution or in developing the simplex method to solve the linear programming problem, but I felt this rank analysis is very basic, and an engineer should always keep this thing in mind very neatly, and that's why I'm mentioning this, that different cases and subcases for consistent different cases and sub cases of consistent system for having unique and infinitely many solutions. The another case is the case of your vertical rectangular system. So the case 2 is the following, is the case where you have m greater than equals to n and the rank of A is equal to rank of the augmented matrix. This is equals to k, and this will then obviously imply k is less than equals to n. K is less than equals to the number of variables, and in this case again you will have two subcases. The first subcase is your k equals to n, and the second subcase is your k less than n. And in this case, for k equal to n, obviously what is happening, k is equal to n means the number of variables and the rank, they are same. For instance, I take here this 2 by 3 system, and the rank, let's suppose it is equals to 2, and 2 is equal to number of variables 2, and therefore there exists a 2 by 2 system uh, for which 2 by 2 submatrix of this matrix 2 by 3, such that that 2 by 2 matrix is having determinant non-zero, and obviously then it will have a unique solution by the Cramer's rule. So there exists a unique solution of the system. And for k less than n, that means if the number of, if the rank is less than the number of variables. For instance, in this system, to sense it, I am giving you this example of 2 by 3. From here you can sense, and then you can generalize to any values of m and n. Here I have taken in particular the value of m is equals to 3 and value of n is equal to 2. And from here you can get the general sense. So if k is less than n, by k is less than n I mean the rank is less than number of variables, and therefore in this particular case you have the rank is less than 2. So obviously then rank is 1 or 0, and 0 is not possible unless this matrix is not 0. Unless, if the matrix is 0, then we call it as a 0 rank matrix, and if it is having rank 1, then in that case what is happening, only one particular row, one particular row is effective and another two rows are just linearly dependent to the first row, and in that case obviously it will again have infinitely many solutions. Fine. And here you note that when you have k less than m, or when you have k less than n, then in those cases you have obviously redundancy. By redundancy, what do I mean here? For k less than n, here note that only in this particular case you had only one equation effective, another two are redundant, and therefore in this case you have precisely the number of rows m minus k many equations are redundant. And here also for k less than m, again you have redundancy of m minus k many equations are redundant. Fine. Well, so these are the exhaustive possibilities of a consistent system for having unique solution or infinitely many solutions. Now let me now try to discuss a particular concept that for a solution that is called a basic solution, which is as follows. Let's suppose a system is consistent. So suppose we start with supposing suppose the system of linear equations ax equals to b is consistent and precisely we let rank of A is equal to rank of the augmented matrix. And here we note that we discussed the theories of linear programming problem where the rank of the matrix, coefficient matrix and the augmented matrix, they are equals to the number of equations. And if it is less than number of equations, then what will happen? The point here is if it is less than number of equations, then precisely if it is equals to k, let's suppose, then precisely m minus k many equations are redundant, and therefore uh, we can again reduce the given system into a matrix of order, into a matrix from A you can convert it to A dash. A was having m by n order and A dash will have precisely your k by m, and then from Ax equals to b you can find a converted system Ax equals to b, for which what you will find that for this Ax equals to b you will find that the rank of the matrix is equals to k, and these two systems in that case will be equivalent, that Ax equals to b and A dash x equals to b, they are equivalent in the sense of their solution sets will be the same. Fine, and therefore instead of considering the discussion where the rank of the matrix A and rank of the augmented matrix is less than m, instead of considering that, we just consider that this system Ax equals to b is having full rank. By full rank we mean the number of rows and a number of rows or number of equations that is identical to the rank of the matrix A and the rank of the augmented matrix. Here you might think, why have I not considered here that the rank of A and rank of the augmented matrix is equals to number of variables? You notice here that if I have a vertical system, that means vertical, but by vertical rectangular I mean this kind of system, in that case you note that you have a problem. What is that particular problem? Problem is that if we have a vertical rectangular system, it cannot have the rank equal to the number of equations, and if the rank is number of variables, then obviously at least one equation is redundant in nature. But what we are trying to consider a system for which there is no redundancy. So if we consider a matrix, so even if we have a vertical system, you can convert it to a system which is rectangular, horizontal rectangular, or a square matrix, which is equivalent to this vertical rectangular system. By equivalent I mean corresponding to any given vertical rectangular system, you can prove that there exists a matrix A which is a square matrix or a horizontal rectangular matrix such that A dash x is equal to B is equivalent to Ax equals to B, due to the fact that once you have the number of variables lesser than the number of equations, then in that case obviously quite a few or at least one equation is redundant in nature if the system is consistent. Fine. And thus there is no loss of generality if we are assuming our discussion of this system where where m is less than or equals to n. Fine. So we consider this system because even if it is not m less than equals to n, but if you are considering it is consistent, in that case you can reduce the system to either a square or to a horizontal rectangular system. Fine. By reduce we mean those equations are redundant, which I have crossed out here, and therefore we are assuming that the given system before us is Ax equals to B with m less than equals to n, and this system is consistent having the rank of the matrix A, rank of the augmented matrix is equal to the number of rows, or it is called as full rank matrix or full row rank matrix. Fine. So let us suppose this, and if we have this, then let us see the scenario what is going to happen. That let's suppose this system Ax equals to B, Ax equals to B is to be solved, X equals to B, and X equals to B can be equivalently written as this is nothing but A1 x1 plus A2 x2 plus AN xn is equal to B. Fine. And you note that the rank of the matrix is equal to A. Once the rank of the matrix is equals to A, there is at least a collection of m many column vectors out of this a1 a2 till an. Out of n columns of the matrix capital A, you have at least one set of m columns which is linearly independent. Then only the rank of A is equal to m, right? So without loss of generality, let us suppose the first m many, or let's suppose not first even if, so let's suppose I have a1 a2 then a5. So there are, let's suppose, m many. This is m many collection. So here is m many collection of the column vectors m many. If the rank of the matrix A is equal to m, then precisely we can find at least one set of m many column vectors which is linearly independent. Fine. Now we choose a set of m many linearly independent column vectors. Without loss of generality, let me take only the first m many vectors, first m many column vectors a1, a2, am. This is linearly independent. Let us suppose this is linearly independent. If this is not, let's suppose if this is my m many linear, let's suppose this is not linearly independent but this is linearly independent, then in that case what we will do is we'll just rename the we'll just rename the column vectors a1 as a1, a2 as a2, then a3 as a5, then am as ap, and accordingly you will find that the first m many vectors are linearly independent, right? So it is just a matter of denotation. Just by changing this denotation a1 x1 or a2 x2, just by changing the denotations or changing the roles of the denotations x1 x2 and xn, you can, without loss of generality, you can assume that the first m many vectors are linearly independent. So we assign the variables which are not associated to these chosen m many vectors, that is linearly independent, we assign in those variable values as equal to 0. Fine. So this will then construct a sub matrix. Let's suppose this sub matrix is B. So let's suppose B is the sub matrix A1, A2 till AM. B is a submatrix of the matrix A, and it is of order m by m, m by m. This is a submatrix which is a non-singular submatrix of the matrix capital A. Fine. And corresponding to these vectors A1, A2, AM, the variables are x1, x2, xm. So I assign now xm plus 1 and rest of the all variables xm plus 2 till xn, those are all equals to 0. I assign this, and then you note that the given system x equals to b can be, now once by putting all these variables xm plus 1, xm plus 2 till xn, putting all these variables equals to 0, this x equals to b will be converted to the matrix b xb is equal to b. Fine, is not that? And this xb is nothing but, here this x you have written in terms of xb vectors, then you have written the vectors which are not associated to the matrix B. Fine. And accordingly bxb equal to b will be the reduced system by putting this variables is equal to 0. And from here you will obtain a solution, because b is an invertible matrix, so it is b inverse b inverse b, and sorry, b inverse b. Fine. And this solution xb is called a basic solution, because this set of linearly independent vectors forms a basis of the column space of the matrix A. Fine. So let me repeat once again how have I constructed a basic solution. You note that we are under this assumption that the rank of A is equal to the rank of the augmented matrix is equal to M. Then we choose, then then there exists an M by M submatrix non-singular submatrix. There exists an M by M non-singular submatrix of the matrix A. Now we set by setting, so let B is such a matrix, such a submatrix. Fine. Now we let xb be the collection of variables, or the vector of variables associated to the column of of b. Fine. So let xb be the vector of variables associated with the column b, and xnb be the vector of variables associated to the columns uh, which are not there in B, associated to the columns of A which are not in B. In B. Fine. And therefore, what am I writing is the variable x, variable vector is, I am writing in this form, xb first, then xnb. Fine. And this, and ax is equal to b is equivalent of bxb plus, let's suppose, the matrix which the column vectors which are not in B, we denote it by Bn, say, or Nb matrix. Fine. Nb is a matrix, they are not two matrices, or let me denote it by some other denotation. Let me say N be the matrix of the columns, consisting the columns of A which are not of B. Fine. So Nx Nb is equal to B. Now putting xnb equals to 0, if we putting xnb is equal to the 0 vector, and here 0 vector, can you all try to think what is the dimension of the 0 vector? 0 vector, how many components are possible in xnb? Xb is having precisely how many variables? Xb is having precisely the number of, xb is the number of variables which is equal to the number of columns of the vector of the matrix B, and B has precisely m many columns, so xb is of m dimensional, so xnb is of x uh, xnb is of n minus m times 1, this dimension, right? So putting xnb is equal to this, we obtain from, let's suppose this is your star gives xb is equal to b inverse b, and obviously this then notice that this xb together with xb is equal to your b inverse b, and xnb xb together with xnb equals to 0. Note that x is equal to xb, then xnb is equal to 0 is a solution to x equals to b, no doubt, right? Because here you had x equals to b, and we know that I can put here xb as b inverse b, and xnb is equal to 0, and this at those values xb is equals to b inverse b and xnb equals to 0 is satisfying this equation, and which is nothing but x equals to b. and therefore this B inverse B0 is a solution to this x equals to b, and this B inverse B solution is coming out from the chosen m by m non-singular submatrix capital B. There can be many possibilities of choosing this capital B. There is at least one capital B. There exists at least one m by m non-singular submatrix of A, but there can be many, and therefore there can be many B matrices, and there can be then many this B inverse B solutions, and any of such solution B inverse B 0 is called a basic solution. It is called a basic solution because it is coming from a basis. Capital B forms a basis. The columns of the matrix capital B forms a basis of the column space of the matrix A, and that's the nomenclature basic solution. Such a solution, such a solution is called a basic solution to Ax equals to B. Fine. And we know that then how many uh, how many variables how many variables of a basic solution can be 0, obviously, or can be non-zero, obviously no more than m. So let me put as a note 1 is that a basic solution has no more than m non-zero variables. M a basic solution has no more than m non-zero variables, right? Because you are putting all the values of all the nb variables, all the variables in nb as 0, and therefore no more than m non-zero variable is possible in a basic solution, or the other way around. In a basic solution, number of non-zero variables is less than equals to m, and we know that is less than equals to m, but there can be a possibility that the number of non-zero variables in a basic solution is less than m, because some of the values of this b inverse b can be 0. In that case, obviously the basic solution is having 0 components more than m. When the basic solution is having 0 components more than m, that is called a degenerate solution. So if the number of non-zero variables number of non-zero variables in a basic solution is less than m, then The solution in the basic solution is called a degenerate basic solution. Fine. And here any variable, so this is a nomenclature, degenerate basic solution, and here any variable in xb is called a basic variable corresponding to a chosen capital B. So once you have chosen a non-singular submatrix capital B corresponding to capital B, we note that corresponding to capital B, obviously you have m many columns. Corresponding to every column of the matrix capital A, you have an associated variable. Corresponding to the column A1, you have the variable x1 associated. Corresponding to the column A2, you have x2, the associated variable, and so on. So once the matrix capital B is chosen, associated variables are also being chosen, and um, those are stacked up. Those are used to form this variable vector xb, and any of the variable in the xb is called a basic variable. Fine. And so a degenerate solution is a solution if any of the basic variable is equal to 0. Fine. And here let me ask you a question, that what is the maximum number of basic solution? What is the maximum number of basic solutions? So here we have a basic solution corresponding to chosen capital B. You have a basic solution. Now what can be the maximum number of basic solutions? You note that that is evidently the number of ways to choose the matrix capital B. The maximum possible number of choice of capital B is obviously out of n many columns. The number of choices to choose m many columns is your n choose m, right? And that is the maximum number of possibilities. So the maximum possible number of basic solution, maximum possible. I'm writing possible because you may have a possibility that not all the submatrices of the matrix, or not all the m by m submatrices of the matrix capital A is non-singular, and therefore the maximum possible number of basic solution is n choose m. Fine. Now let me tell you, let me inform you the result, or before the result let me define one more concept, which is called a basic feasible solution. The basic feasible solution is the following. This is the concept of basic solution, and for basic feasible solution, any basic solution that satisfies the feasibility. By feasibility we mean, and note that we treat this ax equals to b as the constraint, the set of equality constraint in a linear programming problem. And in a standard linear programming problem, apart from the equality constraints, you also have the non-negativity restrictions of the variable. So the constraint set of a standard linear programming problem consists ax equals to b together with x greater than equals to 0. The collection of all x's which satisfies ax equals to b together with x greater than equals to 0 is called the constraint set. And the constraint, if I treat now this ax equals to b as my constraint equalities in a standard linear programming problem, then this is a basic solution, this xb Here this b inverse b together with 0 is a basic solution to the problem, but this basic solution may not be feasible. That means not all the components of this solution may not be non-negative. But if a basic solution satisfies the non-negativity restriction, then we'll call this solution as a basic feasible solution to a given linear programming problem. So I now define the concept of basic feasible solution, or it is shorthanded by BFS. This is basic feasible solution. Consider the LPP. Consider the standard LPP that maximization of C transpose X subject to AX equals to B, and here all the dimensions are as usual. The dimension of C is n, dimension of A is m by n, and the dimension of B is equal to m. All are usual, and also we are under the assumption that the rank of A and rank of the augmented matrix B is equal to m, where rank of A is equal to rank of the augmented matrix is equal to the full rank, and also assume that it is m is less than n. Number of equations are less than or equal to number of variables. Now here in the standard form you also have x greater than or equal to 0. Any basic feasible solution, a basic solution of Ax is equal to B is called a basic feasible solution to this LPP if the solution satisfies if if all the variables, that means your xb greater than or equal to 0, because in the solution you have x and b's are all equal to 0 because it is assumed as a basic solution. So x and b is equal to 0, and obviously it is satisfying then greater than or equals to 0 restriction. So if you have the values of xb in your basic solution greater than or equals to 0, then we call it as a basic feasible solution. So here feasibility, because feasibility is related to not only x equals to b but also feasibility considers x greater than or equals to 0, and that's why any basic solution a of ax equals to b is called a basic feasible solution if that basic solution satisfies the other restriction, that x greater than or equals to 0. Fine, then we call it as a basic feasible solution. Now as I am exceeding time of 1 hour, let me stop here. But more appropriate would have been considering one example and then stop it, so that the idea will be neat. But let me postpone it for the next lecture. In the next lecture then we will start with giving an example of finding basic feasible solution for a given system of linear inequalities. We have described here linear equalities, and the example will be considered for linear inequalities, and obviously for linear inequalities we will convert it to the standard form x equals to b, and we will try to obtain the basic feasible solution. So that will be one example, and from the example we will try to figure out the locations of the basic feasible solution in the feasible region of a given linear programming problem. And we'll find very interesting that the basic feasible solutions are nothing but the kinks or the vertices of the many gonal region or the polytopic region, that is the feasible region of a linear programming problem. Also, after giving an example of basic feasible solution, we will give a result satisfying which we will be able to ensure that all the basic feasible solutions of the problem are all the basic solutions of the problem are basic feasible solutions, and there exist the maximum number of basic feasible solution. So precisely, in order to have precisely NCM number of basic feasible solutions for a given system of linear equalities together with x greater than equals to 0, for that we will try to find a condition on the next day, and then later on we will try to geometrically and try to mathematically characterize the basic feasible solutions. Once the location of the basic feasible solutions are sensed by a two-dimensional figure, then we'll try to go deeper and deeper in terms of mathematical tools to figure out that the kinks or the vertices or the basic feasible solutions are the only possible candidates to be solution of a linear programming problem. With this, let me end the lecture here. I thank you all for all of your kind presence.